us for this second video in the reactions of alkenes. And we're going to be talking about a really central and important reaction today. And it's going to be the addition of either halogens or addition of mercury. And it may sound like two very different things, but they both go through a very similar transition state, or I should say intermediate, and they're of course all electrophilic addition reactions like we discussed. So the general mechanism are going to be very similar to each other. And one thing I might stress that may or may not be relevant to you at this stage, but these reactions are not radical halogenations, which are initiated by light energy or radical initiator reagents. It's not that. So I should not see any single electrons, unpaired electron mechanisms in this. Okay, so without further ado, let's just think about how this might work. So this works with in chlorine, bromine, or iodine halogen by diatomic molecules. Those are elemental molecules, single element molecules, but they're diatomic. And you could think of this as perhaps like an equilibrium thing where the bromine breaks apart heterolytically. That just means two atoms get unequal amounts of electrons in the sort of the breakup of the bond. Right, so that could happen. And now this bromine with a positive charge is called a halonium or bromonium ion. Remember, anything that is a cation ends with ion ion, right? So this is going to be our electrophile in this case, okay? So all of that to say, even before they break up, right, even though they're the same element, there can be quite a bit of polarity difference between the two atoms, and that's because these are fairly large atoms, right? Small atoms, like if they're the same element, there's really not that much of a polarity, but I hope that this makes sense. That right, like if this bromonium cation is an electrophile, it's gonna grab electrons, right, like so, but that's gonna leave a simultaneously developing carbocation one of the carbons, right, and that's very unstable because it doesn't meet the octet. So one of the things that bromines can do, because it does have lone pairs, is to form a bond at the same time. That way the positive charge can be on bromine, which electronegativity wise it's not a great thing to put a positive charge on bromine or halogen, but because it's much bigger atom, it can accommodate the charge. Now you could think of it as what I just drew, but in reality, right, the bromine actually reacts simultaneously with the olefin molecule. So, oops, I want you to kind of think of this as these three arrows simultaneously happening. Okay, now if that happens, I'm just gonna, in this specific case, assume that bromine approached from the front face. So that's what you would get, plus the bromide, right? Now, it's kind of like the protonated epoxide we discussed before, but between the two carbons here, excuse me, the carbon that can bear more of the partial positive charge is the one that's more substituted, this carbon. And so for that reason, if this awkward three-membered ring bromonium ion intermediate would open up to get rid of the positive charge, this bromine wants electrons, so it wants to gain these two electrons to become neutral. But to do so, you kind of need something like an SN2 reaction. So the SN2 reaction is going to happen actually at the more substituted carbon. Now, this is not a normal SN2 because normally, right, you should not expect to see tertiary center undergoing SN2, but this is really driven by the ring opening motivation, because of the angle strain. So it's not the normal SN2, but it is like SN2 in that it does involve inversion of the chiral center. So in this case, bromide would come in from the back, right? And then that's what you will get. Okay, now just as easily, the original bromonium cation could have formed from the front face. So, I'm sorry, from the back face. Then it would have been like so. Again, the positive charge is on more of the more substituted carbon. The bromide is a decent nucleophile that could do SN2 like that, which will result in bromide attacking from the front face. So for that reason, you're going to have a bromide front here, and then the bromide that opened up would be in the back like so. Okay. Now, often we would call these the cyclic bromonium ion intermediate. Or more generically, cyclic halonium cation. Now, as far as summarizing what the product is, we might say there's the, the bromide can come from that face or the front face, like so. But either way, these two I want you to notice are anti-addition product. Okay, where the bromines are, the two bromine atoms are on the opposite side. So in that, for that reason, we would call this reaction stereospecific. It has to be anti in terms of the way that the two atoms add, but it's not enantiospecific because you get racemic mixture of the two enantiomers. Now, I want you to take some time to see if you could predict what the product should be from this reaction. We'll compare answers during class. Now, a slight variation of that earlier reaction, where the solvent was an inert molecule like dichloromethane or carbon tetrachloride, which are fairly non-polar and it cannot participate in a reaction like this. So it didn't participate. But if the solvent is a somewhat more reactive, molecules like water, which is arguably a weak base / weak nucleophile, the reaction will go in a little different direction here. So let's think about that situation. Now, remember, one halogen is going to kind of try to leave, which captures the pi electrons, because one of the chlorines, it's going to act as a chloronium electrophile. But taking the electrons to build a carbocation, it would feel bad. It's kind of like a nice thief that like gets in and robs something, but maybe cleans your house or something like that. That happens. And you're going to form a chloronium cation. Now, you get the other enantiomeric intermediate as well, but I'm just going to kind of abbreviate that as this for now. And plus chloride that left as a leaving group. Now, at this point, right, like you might expect to see chloride coming in and attacking, but if the solvent is water, I want you to notice that the most likely molecule that this intermediate is going to collide with or interact with is going to be that most abundant molecule, the solvent. Now, if the solvent is at least weakly nucleophilic, it could do this ring opening through, of course, SN2. This SN2 step, and what's going to happen, right, is that you get that intermediate. Okay, water has to come in from the other side of the chloronium cation. Of course, the solvent could remove that extra proton. provide you with the product. And of course, throughout this mechanism, there's the enantiomer as well. So what's the product? Well, the product is going to be that plus the mirror image of the enantiomer. I want you to notice this functional group of one having an alcohol right next to a halide. That's called halohydrin. We'll note that. In this case, it's specifically chlorohydrin, which means vicinal OH in halogen. Vicinal means the two carbons that are next to each other have those groups, right? Like I said, this is specifically chlorohydrin. It's going to be the products when the solvent is water, okay? All right, maybe I'll make a note here that water, it's more abundant than chloride. That's the reason for this. Now, likewise as before, I want you to take some time to think about what the products might be from this reaction, and think about the regiochemistry a lot between these two carbons. They're both secondary, but there might be some difference, okay? So some stereospecificity there. Now, this third reaction that we wanted to cover in this video, because they're very similar, the transition state is kind of the same looking, may seem very different because it's got mercury, but hopefully you'll see the similarity in a sec. Now, how is this similar to bromine? Okay, so this is okay, but it looks very different. This is mercury, 2 acetate. Remember that 2 in Roman numeral just means the charge of the transition metal, not the number of things you have. This is kind of similar to the fact that bromine can sort of dissociate a bit, to not very much, but to some extent it could dissociate like this, right? It's kind of like that. The acetate dissociates like bromide dissociates to leave behind mercurinium ion, which, by the way, this group that's abbreviated acetate looks like that. It's one of the polyatomic ions I think you had to memorize for Gen Chem, but okay. So that's why we say this is kind of similar. So you could think of this as like similar to bromonium cation. And what another thing that's similar about it is mercury is fairly electron rich in the valence shell as a metal, so it still has lone pair in it. So as it grabs the, maybe I'll draw it like, as it grabs the electrons, this is going to form 3-membered ring like with a bromonium ion. Okay, so this time let's pretend that this came from the front face, like so. The mercury didn't really gain or lose electrons because it kind of gave 2, gained 2, so it still has a positive charge on it. So I want you to notice how similar that looks to the halonium cation intermediate we saw, because it's really the same. So we could call this a mercurinium ion. Of course, there's the other enantiomeric intermediate involved. Now, this could, of course, be opened up by weak nucleophile. If the solvent is water, no, it doesn't have to be. It could be also an alcohol. If the solvent is water, it's going to attack here. Again, that's the site that has the more of partial positive charge, the carbon that's more substituted. And once that happens, right, so again, this is again an SN2 reaction step. Then the water is going to come in from the other side, and the mercury will be on the other side. okay, like so, with the electrons it just gained. And of course, there's the other enantiomer intermediate as well. Okay, so that's what you get. Now, we could show, I guess we'll show it, using a solvent to remove that extra proton, so it's not charged anymore. It'll be like that. Now, what happens at this point? Well, this is really the product of the first step, and then you have to now follow it up with another step to get a non-mercury containing compound. Organomercury compounds are super toxic. Depending on what it is, you could drop dead from it pretty easily. So that's the product of the first step. The second step, you would treat this with sodium borohydride. Hopefully you remember what that does. That's a good hydride source reducing agent that reduces mercury and form a product that looks like that. So maybe just to show that part of the mechanism. And to be honest, I'm going to kind of show a mechanism that's actually known to be somewhat incorrect, but the true mechanism for this mercury reduction step is fairly complicated. So I just want you to think of it as that, okay? Basically an SN2 reaction with the hydride. This is product of first step. And that will give us the but of course hydrogen doesn't need to be drawn. So now what's so special about this, because this really does the same thing as hydration reaction, if you recall, right? This reaction here where we added the water across the double bonds. I'm showing it like it's stereospecific, but remember now there's a symmetry here, so this is not even a chiral center. What's so special about this? Well, it's special because there's no carbocation intermediate. So that would be the reason why some chemist would choose to do this oxymercuration reaction to introduce water to the double bond instead of the regular acid catalyzed dehydration reaction to avoid a carbocation intermediate. Now, why is that special? Which, by the way, this is still a Markovnikov product. I'll let you think about the product of this reaction where you use ethanol as the solvent for the first step, and we'll compare answers in the class, but let's compare these two situations to think about why this oxymercuration and then followed up by demercuration by hydride reduction matters, right? If you did acid catalyzed dehydration, that goes through the carbocation intermediate, like so. Once the double bond protonates, right? Here's a carbocation. Now, the special thing about carbocation intermediates is that there can be arrangement like this. And followed up by basically an SN1 reaction, you could form this alcohol in water solvent, but there's rearrangement. Now, if that's what you want, that's great, but if you don't want rearrangement and just hydrate this alkene without any rearrangement of the skeleton to, say, in this case, obtain this product, then what you need to do is the oxymercuration reaction. So that would be the difference between just acid catalyzed hydration and this reaction sequence.